Let's find the vector form of the plane 2x plus 3y plus 5z equals 60 in R3. The vector form for a plane in R3 looks like this. X is equal to p plus s times u plus t times v, where p represents the vector version of any point on the plane, and u and v are direction vectors for the plane. Now it's important to mention here that u and v should be non-parallel direction vectors. Let's see with a sketch why this is important. Let's say we've got a plane here. We can describe this plane by taking any point P that's on that plane and describing two different direction vectors that lie in this plane. So by starting at this point P and by taking linear combinations of these vectors u and v, we're able to travel to any other point on the plane. Now it's important that u and v are not parallel because if, for example, we start at this point P and we choose two parallel vectors u and v, maybe v is longer than u in the same direction, maybe v is going in exactly the opposite direction. In this specific case here, we would only be tracing out a line in R3 rather than the whole plane. So I'm going to scribble over this and show this is what we do not want to do. So let's look back at the general form that's given in the question, 2x plus 3y plus 5z equals 60. And we're going to use this general form to find 3 points that lie on our plane. So geometrically, let's call these 3 points P, Q, and R. We'll be able to use Q and R to build our two direction vectors u and v. All right, so let's write down our 3 points. Often the easiest way to find these 3 points is to let two of your variables be 0. So if we let x and y be 0, this general form here collapses down to the equation 5z equals 60, and that tells us z is equal to 12. So that gives us 1 point on the plane. Similarly, letting x and z be 0, our equation looks like 3y equals 60, so y must be 20. And letting y and z be 0, we get the equation 2x equals 60, so x must be 30. So there we go, we've got 3 points on the plane, and we can choose our direction vectors by saying, hey, why don't we let u be the vector pq? Algebraically, we're going q minus p, so we're getting the vector 0, 20, minus 12. And we can let v be the vector pr, so algebraically we're going r minus p to get 30, 0, negative 12. And we can just do a quick check here that u and v are not parallel. We know that they're not parallel because these two vectors are not multiples of one another. So we've got a point P that lies on our plane. We've got two non-parallel direction vectors, and we're all set to plug in to our vector form up here. So looking back up top here to our vector form, let's plug in. X represents the vector x, y, z. Vector P here represents the vector form or the vectorization of the point P. So let's write 0, 0 is 12. And then we're going to go plus s times the vector u plus t times the vector v. And there we have our vector form. It's important to mention that the vector form is not unique. So you may well have made a different choice of P, Q, and R. If you did that, then this point here, this point P may well look different. These vectors here may well look different. So there are many other possible correct answers. Now I wanted to briefly mention the parametric form. for a plane in R3 because it is related to the vector form. So although it wasn't asked for in the question, let's just have some final comments about parametric form here. If we were to look at the individual components of these vectors here and set up one equation for each component, for example, write something like x is equal to 0 plus 0 times s plus 30 times t. Well, in fact, this is a little bit cumbersome of way to write it. Normally, we would just write something like x is equal to 30t. Y is equal to 20s. Z is equal to 12 minus 12s minus 12t. Setting up this system of equations here gives us what is known as the parametric form for the plane in R3.